Hello dear friends, welcome to a lecture on ring theory. Today in this lecture we shall study ideals of rings, its definition, some examples and a few problems also we shall solve on ideals of ring. I have written definition of an ideal of a ring. A non-empty subset U of a ring R is said to be a two-sided ideal of R if there are two conditions. First is U is subgroup of R under addition, and second is for every U belongs to U and R belongs to R, both RU and UR in U. So this ideal is said to be two-sided because there are two types of ideal, left ideal and right ideal. If U is first thing is U is a subset of R. See, U is subset of R, and then the first condition is U is subgroup of R under addition. That means this U plus with respect to plus operation is a group. It must form a group. And the next thing is for every element in U and R in R, both this product RU, this condition RU belongs to U is for left ideal. Left ideal. This is left ideal of ring R. And second condition U into R. U is in U, R is in R, but their product is necessarily in U. So this is the condition for right ideal. And because we have written both these conditions in this definition, so therefore this ideal is known as two-sided ideal, means both left as well as right ideal. So this is the definition of ideal of a ring. Now the two conditions are this one: U is subgroup of R under addition. How to prove U is subgroup of R under addition? To prove a subgroup we need a closure property. We earlier studied in group theory subgroup. So we say H is a subgroup of G, a group G. If closure property is satisfied, that means A, B belongs to H implies AB belongs to H. And second condition is for inverse. And in that case, A belongs to H implies A inverse belongs to H. But these two properties together can be combined, and it is sufficient to prove that if AB belongs to H implies A into B inverse belongs to H, then it forms a subgroup. Then we say H is subgroup of G. The same condition we shall use to prove U is subgroup of R. And for that purpose, if you consider two elements, let's say A and B belongs to U, then this must imply. So what this will be? A into B inverse. The composition here is product, but this is under addition. So therefore the composition here will be addition, and the inverse of B is additive inverse of B, and that will be A minus B. So this must belong to U. So that will be the first condition. So we shall write it as that U is subgroup of R. U is a subgroup of R under addition. Under addition, if AB belongs to U, that is simple, and both these conditions are combined in this one condition, that closure also as well as inverse also. So this is a closure, and this here is inverse. So this is a result in group theory. You may refer that lecture. And AB belongs to U implies A minus B belongs to U. That is the first condition. And second is direct, that is U is an element in U, R is an element in R, ring. And then the product, both product RU and UR must be in U, then U becomes ideal. Now we shall consider some examples of ideal. ideal of a ring. And now the trivial example we shall consider first as, let R be a ring, then singleton 0 and R itself are ideals of R, and these will be trivial ideals. We shall see these are ideals of R. This singleton 0 is a subgroup under addition. So because it contains only single element 0, and how to prove it is a subgroup under addition? Because it contains only 0 element, and then if 0 and 0 in U, then 0 minus 0, 0 is element of U, and then this implies 0 minus 0, which is 0, belongs to U. So therefore this is a subgroup under addition. And second thing is that is 0 is in U, and take any element R in R. See, any element U in U, here this contains only element 0. So 0 in U, R in R, and this implies 0 into R or R into 0, which is 0, and that is in U. So therefore 0 is an ideal. Both conditions are satisfied. It forms subgroup under addition and it satisfies this second condition also, and therefore 0 is an ideal of ring R. And R itself is an ideal because R is subset of R. R is subgroup under addition of itself, and then if U is in R and again any element, any two elements of R, this is a closure property, and therefore R itself is an ideal of R. So this is trivial ideals. These are trivial ideals, 0 and R itself. 0 and R are trivial ideals or proper ideals, trivial ideals of R. Now we shall consider some non-trivial examples. As second example, let R be a ring of integers, all integers, under addition and multiplication, usual addition and multiplication. Let a ring of all integers. Usual addition and multiplication. And further we shall form, let U be the set, or before considering the set U, let M be a fixed integer. And let now we will define U as U is equal to, say, Rm, such that R belongs to R, ring of integers. R is an integer. Then we shall see that this is an ideal of ring R. Now how? Because first thing is, now we shall prove U is subgroup of R. Subgroup of R under addition. Now to prove this, we shall use this condition. Take two elements in U and show their difference, the other A minus B is also in U. And let us consider two elements in U as, see, R is varying here, M is fixed, and therefore two elements in U can be taken as R1M and R2M. Let R1M, R2M belongs to U. Now what we have to prove is that R1M minus R2M, and this we have to prove is in U, but this can be written as R1 minus R2 into M. And what is R1 and R2? R1 and R2 are integers that are in R, and R1 minus R2 is also an integer, and therefore this is an integer multiplied by m. Integer multiplied by m is an element of U. So this belongs to U, since here R1, R2 are integers, and therefore this is also an integer multiple of m. The meaning is this is the set of integer multiple of m, and thus this belongs to U, and therefore U is subgroup of R under addition. Therefore U is subgroup. First condition is verified, subgroup of R under addition. Now second we have to check this condition. Let U belongs to U. Take any element of U, any element of R, and show that the product R into U and U into R is again in U, and therefore we shall consider an element in U, and an element in U we will take in the same form, Rm. Let Rm belongs to U. R is integer, and further let see, one element we have to consider in this and another element we have to consider in the ring, and that another element in ring we may consider R1, and let R1 belongs to R. Now what we have to show, their product, the product of these two, that is Rm into R1 and R1 into Rm, is again in U. That we have to show. Now, or we may consider first R into U, element of R and element of U. Element of R we have taken as R1. So R1 into Rm, this is. And this is a ring of integers under usual addition and multiplication, or usual multiplication is to be considered, and we know that usual multiplication is commutative and also associative. So therefore this can be written as R1R into M. And you see, R1 is integer, it is a ring of integers, and R is also integer, their product is integer, and therefore this is an integer multiplied by M, and therefore is an element of U. So this belongs to U. Also what we have to consider is Rm into R1. Two-sided ideal we have to show. U into R, element of U into element of R, element of U and element of R. And this further can be written as, see, we can write this as Mr into R1, because this is commutative. Usual multiplication is commutative, and therefore we can write Rm as Mr. And again using instead of that we can write M_R1. So because we want M as the second factor, so therefore this can be written as R M_R1, and then this as R_R1M, and then this as R_R1 into M, and again this belongs to U. See, because this is integer and this is multiple of M. So therefore this satisfies the second condition. Both these elements are in U, and therefore this U is an ideal of R. Thus U is an ideal of R. Or simplicity, for simplicity we shall consider particular example of this. R is ring of integers. Here we have R is, what is R? Integers, all integers, and therefore that can be written as 0 plus minus 1 plus minus 2 etc., all integers, and so on. So what is U? I take M be a fixed integer. Let us suppose M is equal to any integer, positive, negative, etc. We shall suppose M is equal to 5, and then what will be U? Then U is equal to that is R into M, or that is 5M. r into 5 or 5 into m, and because no, it is 5r, m is taken as 5, so 5 into r, or that is 5r. So r is integer, and r is integer means r belongs to this r, and therefore multiple of 5, multiple of all integers, multiple of 5. So multiply this by 5, what set we shall get is 0, plus minus 5, plus minus 10, plus minus 15, and so on. And this u is an ideal of this ring of integers. That means the set of all multiples of 5 forms an ideal of set of ideal of ring of all integers. Similarly, we can consider instead of 5 as 3 or 7, etc., any multiple. So infinitely many ideals can be formed for set of ring of all integers under multiplication and addition. So this is an example, and these properties can be easily checked. If you consider any two elements of u, then their difference, this is a difference of this, is again a multiple of 5. So the subgroup property is verified. And take an element of this u, multiply it by any element of r, then the product also belongs to u. Because if you consider this as say an element as this one, and take an element as this one here, if you multiply these two, the product is plus minus 30, and plus minus 30 is an element of this, it is multiple of 5. So therefore this second property is also satisfied, and thus this is an example. This is an ideal of the ring of all integers. Now we shall consider some problems on ideals of rings, and see, the problems are also simple. The first problem we shall consider as let u be an ideal of ring R, and R here we shall not write ring, but R means ring. U be an ideal of R, and let if further if 1 belongs to U, then U and R are equal. This is the result. If one unit element, U contains unit element and U is ideal of R, then that ideal is equal to the whole ring R. That is to be proved. Now the solution for this problem. It is given that U is ideal of R means U satisfies these two conditions. Now we know that an ideal is subset of subset U of R. See, we have U is ideal and therefore U is subset of R. To prove the equality, what we need to prove is R is also subset of U. If the sets are subset of each other, then they are equal. So we shall prove R is subset of U, then the two becomes equal, and for that purpose we shall take any element in R. Let R belongs to R, and 1 is in U, that is given. See, 1 belongs to U. Now by the second property of this condition of this ideal, what we must have, their product must be in U. So what is their product? R into 1. Then since U is an ideal, R into 1 is equal to 1 into R, or which is R. This must belong to U since U is an ideal of R. And see, R belongs to U. So what we have here, R belongs to R, and what we have again, R belongs to U, means every element of R is an element of U, and this shows that therefore R is subset of U, and this proves the result. R is subset of U means U and R is equal to U and R are equal, thus U is equal to R. So it is easy. Now second problem we shall consider as if F be a field. if F is a field, then the only ideals of F are 0 and F itself. That means trivial ideals. This we have to prove. Now the solution for this. So 0 is an always ideal of any ring. So F is filled, it is a ring, and therefore 0 is ideal of F. So we have 0 is an ideal. It is a trivial ideal of R. R here is filled of F. F is also an ideal of F itself. But what we have to prove that only these are the only ideals of a field, and that means it does not contain proper ideals, so which are not equal to F and 0. So that we have to actually prove. 0 is an ideal of F because 0 is a subgroup under addition that we have seen in our first example, and also any element 0 belongs to 0, R belongs to R, their product is 0, and therefore it is again in the set 0, and therefore the first condition and the second condition also satisfies. Now let U be any non-zero subset of F. Non-zero, or we may consider non-zero ideal, and that will be subset. Non-zero ideal of F, field F. Then, because we know that every element in a field has, every non-zero element in field has multiplicative inverse. Every non-zero element of a field has multiplicative inverse. Now see, we have considered non-zero ideal of F, and see, it is ideal means it satisfies both the conditions. So U is a subgroup of R under addition, and this condition is also satisfied. And let R belongs to U, R which is not 0, R not equal to 0, and R belongs to U, non-zero element in U, that we shall consider. And if it is an element in U, see, it is an element in F because U is subset of F. Then this implies R belongs to F, since U is ideal and ideal is subset of a ring. See, subset, U is subset of R, and R belongs to F, R is non-zero, and F is filled, therefore this R has multiplicative inverse. This implies R inverse belongs to F. And again, what this will imply, these are both the elements in F, and by closure property its product must be in also F. So therefore R into R inverse, which is equal to 1, belongs to F. And thus we have the unit element in F. If 1 belongs to F, then this F is that will form an ideal. So again we have this 1 belongs to not in F but in U. See, the product must be in U. So therefore this 1 belongs to U, the product of this. So what we actually we have to consider is R belongs to F, R inverse belongs to F, R is in U. See this product, R is in U and R inverse is in F, and therefore their product is 1, and the product of these two elements is in U. U is in U, R is in R, their product is in U. So therefore the product of these two elements is in U, and thus 1 belongs to U. And once 1 is an identity element or unit element is in the set ideal, then the ideal is equal to the whole ring. So therefore that is our first example. You see, 1 belongs to U, then U is equal to R, and here 1 belongs to U, then this U is equal to R. Here is filled F. So therefore this U is equal to F. Also, or we can write like this. Also, if you consider R belongs to F, then 1 into R. See, R U is 1 is in U, and then this R is also in U, and 1 into R is again in F. So thus this shows that U is F is subset of U. So or here we can consider it is in U. 1 into R is in U. So F is subset of U. And U is subset of F is subset of U, therefore U is equal to F. And thus you see, if F is a field, then its only ideals are 0 and F itself. Now the third example can be considered as this one. Third problem we shall have. Let R be a ring, commutative ring. And let A belongs to R. A be an element in R. We shall consider AR further. AR is equal to AR. R belongs to R. These are the elements, multiple of A. Then this AR is an ideal of R. Then we may prove that AR is two-sided ideal. Because it is commutative, it will be two-sided ideal of R. Now that is similar to earlier example that we have considered RM. M is fixed. Here what is fixed? A is fixed, and therefore AR will be an ideal. See, it is easy. First is subgroup. We have to prove that AR is subgroup under addition. See, the solution for this, AR is subgroup under addition, and for this purpose two elements in AR can be taken as AR1. Let AR1 and AR2 belongs to AR. What we need to prove is AR1 minus AR2. Then this implies AR1 minus AR2, or A is common, R1 minus R2, and this belongs to this set because R is an element of R. R1 minus R2 is also an element of R, and therefore this element belongs to this set AR, and this proves subgroup. Now what about the second condition? Take an element in U, that means this set. Let AR belongs to AR, and let R1 belongs to R. An element in R, element in this set to be proved as ideal, and any element of the ring is R, and their product we have to prove is in the ideal AR. So then now what is their product? AR into R1, AR into R1, and that can be written as A by associative property, A into R1, and these two are integers. R is integer, R1 is integer, not integer but element of R. we have earlier considered an example of set of all integers, but here it is given as any commutative ring, and therefore this is an element, both are element in R, their product is also in R, and therefore this is an element of AR. Also, now we have to consider R1 into AR, and because the ring is commutative, we can write this A as first factor, and this can also be written as A into R1R, and this belongs to AR, and thus AR is an ideal of the commutative ring R. So thus we have proved that this forms also a ideal. Now one more example I shall tell you to solve yourself. Let U and V be ideals of, or two ideals of R, of a ring R. Then prove that U plus V, which will be U plus V. U belongs to first ideal and V belongs to second ideal. V is an ideal of R. Now how will you prove this? Prove these two. Subgroup first. U plus V is a subgroup of R, and that means U plus V is a subgroup of R under addition, subgroup of R under addition. So that is to be proved. Take two elements of this type. And how to take two elements of this? U1 plus V1, small u1 plus small v1. U1 belongs to U, V1 belongs to U. And take another elements as U2 plus V2. Show their difference belongs to this same set, that is U plus V. It is easy. And now further what is to be considered is take an element, same element U plus V, and take an element in R as R. So then what we have to prove? R into U plus V, and this belongs to U plus V into R, and this both belong to that U plus V. That is to be proved, and it can be proved easily because of distributive property. Because what will be this? RU plus RV, and see, because U is an ideal, RU is in U. So this is in U, and because V is an ideal, this is in V, and therefore the first element is in U, second is in V, their sum is in U plus V by definition. So in that way we can prove both these results, and first also is obvious. One more example you may try is, see, that is fifth example. Let U and V be ideals of R, and further let U into V is equal to this finite product sum of finite sum of the product Ui Vi, such that Ui belongs to U, Vi belongs to V, where the summation is finite. Prove that UV is an ideal of R. Likewise, we have to prove two conditions. First is UV is subgroup of R under addition, and this summation is finite, 1 to n you may consider. And then second condition is this one: take an element in UV, take an element of R, that is that can be considered as R, and show their product is in UV. So here two elements can be considered as, say, one element sigma Ui Vi, another element Ui dash Vi dash or prime. So these are two elements in this set, and their difference is also in the same set, because the difference can be expressed as summation of ui vi minus ui prime vi prime. And see, this is also again of this type. It is the product of the elements in ui and vi. It is negative, or we may have this as u1 v1 etc. up to un vn, finite sum, and this will be minus u1 dash v1 dash plus so on up to un dash vn dash. And you see, plus it is additive inverse. Additive inverse, it exists, and therefore this is an element. This may be written as plus of negative of this, and therefore this is an element of uv. Likewise, you may consider r is in r, and the product r into summation ui vi, and that will be summation r times ui into vi. And because u is an ideal, this is an element in u, and this is an element of v, and therefore this also belongs to uv, and this proves uv is an ideal of r. So please try these two examples yourself. Try to solve these two yourself. Thank you for watching the lecture. Remaining part we will continue in our next lecture.